We were already live.
Nice.
All right, welcome everybody. My name is Ben Partida, the current president of the Robotics Society of Southern California. This is the July meeting of 2025. Today we have some great talks. One of our youngest members, Seth, will be giving his first debut lecture, which we are all very excited about. Yep.
Board member Seth.
Yeah. Oh, yeah, board member Seth, that's right. Yeah, and
He's not.
so the way that the meetings work, we usually have two lectures in the morning. Then we break for a short lunch. After lunch, we come back and it's a show and tell, which is one of the best parts of the club, where everybody and anybody can bring in stuff and show it off, tell us what they're working on. After that, it's just a open mic and open discussion. We can talk about everything and anything. So with that, you guys, is Seth up first or?
Yeah.
All right, Seth,
Start sharing.
You turn
go
off
for it, buddy.
He's not allowed to screen share.
Oh. Sharing.
Yes, the computer audio, sorry. Darn.
You want to share your video to your camera? Okay. I understand. No worries.
We can start sharing.
Saves bandwidth.
That's
That's
asking
what
a lot.
it saves bandwidth.
Yeah.
All right, you go ahead and try again.
All righty, there we go. Way bigger. Yeah, I need speed. Bigger. Yeah. I think that's better. One or two more. Just several people here. Not me. There we go.
Oh, your eyes are good.
No.
Oh, it's not bad.
It's very good.
I think this is for everyone else.
Yeah, there's a dopey. Alrighty.
Yeah, that's why I have my whole piece to do.
That'll be yours.
Yeah.
So much
We're talking about that.
But then it's.
Okay, so today I'm going to be talking about this pretty cool AI tool called OLOM.
Yeah.
And so basically it allows you to run large language models kind of similar to like the OpenAI ones like GPT-4o entirely on your computer offline for free. So yeah, let me show the website. So on their website, you will be able to find where to download it, which will be different depending if you use Mac, Linux, or Windows. And then you can find models you can download. Yeah, want to go back. Okay, so the first part I'm going to go over is downloading models and what can you actually run on your computer. So
Actually, go back to this. You talk about installing and everything, because that's, and you have a lot of words that we didn't talk about. Huh? Wait, go back. Oh, no, right here, because you're talking about you can run things locally, like with or without a GPU, you can run on Mac, Linux, all those things.
okay, so I'm gonna step back a moment. So OLAMA allows you to run these models using pretty much any hardware for acceleration on pretty much any platform. So like on Windows and Linux, if you have an NVIDIA or AMD graphics card, you can use CUDA or ROCm. And even on Mac, it actually supports Apple's Metal like architecture for acceleration. Assuming you have one of the newer Apple Silicon Macs. Let me try again.
Just keep going to your thing.
Okay. So OLAMA, you can download OLAMA models from either their website, the official one, or Hugging Face. So I recommend using their website just because it's typically simpler and easier to find actually supported models that are higher quality. So, like I said a moment ago, you can use a lot of features similar to OpenAI or XAI, or I guess Anthropic also.
Sure.
Okay, so the one problem with Olama is that it can take quite a bit of resources, and it can be a little difficult to figure out like if a model will run and if it'll run well on your hardware. So for me, the easiest way I usually handle it is I just check, if you go to their models, let's say Demo 3N, I just check the size of the model and compare it to my graphics card. Oh, geez, my scrolling is bad. So I have an 8 GB card, so I would probably be able to get away with using the full 4 billion mixture of experts model. Although you do want to leave a little bit of VRAM for your context, and depending on your computer, you may also want to leave some for your actual desktop.
So I said, what if you don't have a graphics card?
So if you don't have a graphics card, Olama will automatically just run the model on your CPU and use your regular RAM,
Oh, okay.
which is slower because regular CPUs are not designed for a lot of floating point math, which AI models typically use. But it still can run pretty well. And you were trying the demo model and got like 5 tokens per second on an i5, so
Like 7.
that.
Okay, and you get like what, 60 or 70 on the GPU?
Yeah, and I'm using a 4060, so it's not the highest end GPU. You can really just use whatever you have already. So if you're downloading from Hugging Face though, they have their own way you can do that. So I can actually show if I find a model. Ooh, like make it big. Ooh.
Control shift area.
Here you go, that's 200 scale. So Hugging Face has a tool where on the side, I don't know why it won't let me zoom in on it.
Yeah, mirror. Yeah, all right.
It's that readable, it's a little better, I guess. On the side, it'll tell you the different quantizations and how much storage or RAM it'll use. And give you a little check mark on if you can actually run it. And I think,
So what's happening there, you told it already what hardware you have, right?
yeah,
And it's comparing your hardware specs to the model requirements and gives you a great idea of which one you can use.
Oh, can you show me how you did that? I didn't know Hugging Face did that.
okay, so it's a little weird. You will need an account. Luckily, making an account is free. But you'll just click on your profile. Oops. You can go to settings, local apps and hardware, and then you will be able to select that you're using Olama, because I actually learned this like a week or two ago. If you have an account, they will automatically turn everything off now. So you won't see the Olama command option. And then you can add whatever CPU, GPUs, or Mac you have. And it'll automatically show up here along with the option to, and I should probably move this a little bit. To click use this model, and it'll give you a very just copy paste command to run the model, and it'll download it for you.
If you have more than one
Yeah,
machine.
yeah, I mean, because everyone's wondering, can
you
I
have more
run
than one
this model,
machine,
can I run
you
that
change
model?
profile.
Yeah, usually
It'll
just
run on
push
this
the number and I say, well, that looks like a fit and try it.
I'm not sure if they support that. I don't think so. I think they designed it so that whatever your best hardware is, you're supposed to put in.
Most different profiles, like,
Yeah.
I have a, standalone box and I
That's
have a
what I
PC.
Yeah, by 3080 versus my Mac.
Yeah.
That was nice.
So you have to switch it or have different accounts.
So here you would check, you would choose that 8-bit one because that fits.
Yeah. Or maybe the 16-bit, it's a little higher on RAM usage, but it would work.
Oh, so yellow check is like maybe?
Yeah, otherwise it'll show, and I don't have it here. It'll show a red check if the model is just way too big for your computer.
It'll run, but don't expect to check your email.
Right.
And this actually goes to what I'm gonna say next. In some cases, you might actually still want to use a really large model for some reason, even though your hardware is not really fit to run that. So, from my experience, Olama will try and offload layers to the CPU, but still try and use the GPU for as much of the processing as it can. So at home, I was able to get my RTX 2060 to reliably run a 30 billion parameter model plan. It was running, I think, like 15 tokens per second, which is not bad
Usable, kind of.
and somewhat usable. But then there's also, I would like to take a moment to explain the quantization, which is a lot of how Olama actually works, where they take like a full model and, for lack of better words, they basically simplify it into a less accurate but a lot smaller version of the model, which takes less space, RAM, and processing power to run. So if you go to their, no, that's not their website, I don't know why I thought that was. If you go to their website, a lot of their models, like if I go to DeepSeek, it should show me. Yeah, here, it shows quantization Q4KM, so it's 4-bit, which most of their models will run unless they're very young. But if you download them from Hugging Face, like I showed, actually I'll show it here because
I know what all those letters mean, Q, K, 4, M. I don't know what those mean.
Okay, so the Q just stands for quantized. And then the really important part is whatever number comes after. So like Q4 will be 4-bit instead of your regular 16-bit, where the F stands for float, for floating point.
Any idea what K and N mean? Okay, that's fine. I don't know what it means either.
I'm not completely sure.
Okay.
No.
I know the K and M ones are usually more accurate, I believe. They take more space. But if you download from Hugging Face, it does support for any model, or any supported model, I should say. It will run in any quantization down to like 2-bit. I think it might run 1 or 1.5-bit models, but I haven't tried it, and it's, when I do try those models, it's just kind of bad right now.
Is there a sweet spot that you found, like floating point works is the best, I suppose,
Yeah.
and then 16-bit is noticeably different or not noticeably, like how far can you go down before it starts messing up?
16-bit is usually the standard. At this point, models are usually trained in 16-bit. But I'd say the sweet spot is 4-bit, because it maintains a lot of the actual quality of the model, but makes it way smaller. But if you have the hardware, I recommend 8-bit just because you get a little more accuracy while not losing as much. And lastly, for this part, I'd like to go over some of the simpler commands, the essential commands that Olama has. So the first one is Olama run, which I can actually show right now. Here, we'll use the one that's auto-completing for me. So you'll be able to.
Sorry, quick question. So these different models, are the differences only the way it's represented, or is it also what they trained it on?
So,
I can answer that both.
Both?
yeah,
So the different families of model are probably trained on different corpuses, and then within a family, that there's different sizes of like how big the model, how many parameters it has inside of it. Does that sound right?
Yeah, so like when 4B and 4 billion and 8 billion, I should say, are going to be like the same training data, but one is a shrunk down version. So if I run that, it might take a moment to load, but it will. If necessary, it will download.
And that's just a regular command line you're running there. It just looks funny
Yeah.
because you're in VS Code.
Yeah, I have like fancy stuff installed, but it's the same as if you were using Windows or Bash or whatever. So you can see I can do a simple chat with it just in the command line fields. You see, sometimes it takes a little while because this is a thinking model where basically it'll think before it actually writes anything. Similar to like OpenAI's O3 model. Then you have Olama Poll will do the same thing. I don't think I have a good model to show that. So that one should be fast. It's the same thing, except it'll only download it. It won't actually run it for you. Yeah, I'm gonna cancel it. That's it.
Yeah, I know it. You were 20% already, dude.
You don't need that one. That was like the worst model I could think of at the moment.
But that goes up to the registry, grabs the model, pulls it down locally, and now you're ready to run it locally. So it's pretty painless.
Yeah. Then another helpful command is olama list. You can see I'm a mess right now, but you can see the different models you have downloaded. And then lastly, you have olama show, which is actually kind of helpful.
Sorry, real quick. So this is all can be done offline?
Yeah, everything except run if you're downloading, and poll is always going to be online.
Okay.
But once it's downloaded, run all day long with no internet, right?
Yeah, I would show it except I'm on Zoom.
Yeah.
So here, if I run the show command, you can see it tells me the architecture, shows me how many parameters, the context and embedding length, the type of quantization, which is pretty mean. It shows me that this is a completion model and it supports tools and thinking, and then some of the default settings here. So from there,
Can I change those settings? Can I like change the temperature?
okay, so the easiest way to do that is either, I'm gonna show it next when you're actually programming with it, or if you're doing Olama run, you can do like set, I think this is right. Can't spell. I put it on. I think it's set parameter. I don't use it often. Okay, there we go. So you have set parameter and you can change it just for the session. It will not change the actual file. Otherwise you have to, and you can look into this, you have to create a model file for it. And then it'll be a second custom model, which is just kind of weird and confusing. And honestly, not very helpful unless you have a custom model. So here, I'm gonna close this because I don't need it for now. So the next part I'm going to go to is, okay. So the next part I'm going to go to is using it with, like when actually coding it. And in this example, I'm going to show the OpenAI API. For people. Oh, yeah, that worked. Okay. So I chose to show with the OpenAI API because it is the most common. And especially if you already wrote a program that probably uses it, it's easy to show how to switch to Olam.
So this is what I would use if I'm using OpenAI, I pay for it and everything. I use this API, I get an API key, and I can start using it. So that's the API you're using, but now you're
Yeah.
faking it out, right?
Yeah, so what all you have to really do to change to Olama is set your base URL to this, to your local host with the Olama port. Something both me and Alan had an issue with is you have to put the /v1, otherwise it just won't recognize it at all. And also, for some reason, OpenAI does not document the base URL parameter very well. Because I Googled for a while, I ended up having to ask ChatGPT how to do that when I was first getting started with
So
it.
you just ran that and now you got your client ready to go, right?
Yes, also you will be required to put an API key, even though Olama doesn't use one. So I just made up a fake one for fun.
Definitely
Just
real.
give it one for forever. Okay, so next part, and I don't know why I didn't fill that out. But, so the next part, I'm going to show how you can actually make a chat completion with it. And since I didn't write it, I'm gonna go over it anyways. There's 3 types of messages. There's the system, which is how you want the AI to act. So here I just gave it its name and it does that. I give it its name and how it's going to speak. User, which is any message from the actual user or whatever you're giving to it. And assistant, which is a message from the chatbot itself. So here I define chat and then I tell it to get a response and print that response. So you can see, might take a moment because it has to load the model. If the model isn't loaded, the cool thing is that it'll load it automatically as long as it's on your hard drive. So you can see it responds pretty quickly. Should I add anything or should I?
Yeah, I mean, you can play with it, you can ask it more questions. So I mean, so this thing, you gave it the system prompt and you gave it the user prompt. And you can change that to anything you want. That could be tell me a joke, it could
Yeah.
be.
So you can. So I can change it to like use a lot of emojis.
Just chilling here. That's funny.
It's pretty cool. You can do a lot of really cool stuff with that, both for fun and for actual useful purposes.
And that's a 4B model, so it's pretty small, right?
Yeah, 4 billion. And it also supports vision, which I'll show later in this notebook. For my next demo, it's a little longer, but this one I show how you can use multiple terms and the models can actually memorize and have a full conversation with you. So here you can see I only give it the system prompt. Then I give it the user message, which I'll show.
Go slowly line by line, there's a lot of stuff here.
So I get the user's input. Then if I don't put anything, I want it to end the loop because otherwise I'd have to reset the whole Jupyter notebook. So then I put it in the output so that you can actually see the history. I add it to the actual history. And then I give that similar to before I give that to the model to actually run. Real quickly, I'd like to go over what temperature is because I've referenced it a couple times now. So the temperature is used when it's actually picking what token to output next. So something low like 0.1 will pick whatever it thinks is the most likely, or one of the most likely. If I set it to something like 1.0, it'll try and pick a little more randomly than just picking the top whatever. It all sets to 0.5 does. And then I add the assistant response from the AI to the chat and I print that out. Here I can run it.
There's a temperature where you probably would get the same response every time.
Yeah, I believe with Olama you can do I believe 0.0 and it should always be the top token.
Okay.
So what should I ask it?
Someone,
Is,
let's chat with it, what's the?
How many salamanders live in the United States? How many species?
they say, like for the Google, the search results, do they anyone know like what the temperature is on that? Cause you would expect it to be 0, or you would expect it to always be the correct answer. That's your assumption when you see those results.
Interesting use of the
But the
word.
fact that it might be random.
You know, it's interesting, so at work, we don't use zero temperature, even though we have an industrial application.
Yeah,
You go, because I guess it just gets too constrained and too, I don't know what the problem.
Too literal, yeah.
Too literal.
Yeah.
yeah.
Out there.
Gotta give it some creativity, you gotta allow it.
Yeah, was it? I mean, you do that with humans, I guess, but
Yeah.
still.
Well, it's still waiting for our
You're
message,
boxing
so-
it in if you put it too low.
Wait, my name. Seth, so I'll give it something to remember here. You see, it says, "Hi Seth, it's nice to meet you." So then I can ask, "What is my name?" And
It's
then
just
you
on
can
the
see
here,
it,
by the way.
Perfect.
you can see it remembers details from earlier. Let's see if it
Oh,
remembers.
we're still in emoji mode?
Yeah.
Not using, I believe, default, yeah, I'm just doing friendly and concisely.
Oh,
but
very
get
friendly
short.
as you emojis.
Yeah.
So, question, so, how does it remember? That it sort of implies that when you do that chat append, it's appending the message, and then does it send every time it sends the full history?
Yes, so I have a full history, and then every time I send a message or I receive a message, I add that onto the history.
Can you show us the line of code?
Yeah, the line of
That-
code for that, or,
Because I think that's a real key thing,
Yeah,
that
start with-
you're building up this user system, and you pass that back every time, so it's getting longer and longer.
yeah,
So you can see I use the same format I usually use, and I just put the user message here.
now does
And
it,
then that always gets re-sent.
And then also, when it gives you
And the
the
next
answer,
one.
you do chat dot append what the assistant came back with, right? So you have a full chat
so there's a
history.
pair.
Oh, so you're
Every-
adding on to it every time you call it?
Every interaction, there is a pair of turns. Right, this is what, yeah, I'm working.
Yeah,
with
because
too.
otherwise it'd be brain dead, it would remember anything that happened, right?
Yeah, so Seth, I see like system and user and assistant, what are all those? Like, why, what do those mean?
Okay, so the system is the prompt you give the AI for like how it's going to act or what it's going to do. So here I just have it act like a chat bot. But you can also use it to tell it like, convert this to this format or summarize whatever's given to you. Basically whatever you want to do. And then a user message is whatever input you then give to that AI. And
So-
it'll
so-
respond with an
We
assistant.
always say he's friendly, but I could say you're a snobby teenager, or, you know, I can say, and then have it act like that, right?
Oh, yeah, Nurse Ratchet.
That was really good.
Can the user override this? Setting, so like, should I copy and override what the system function?
It depends, because some models will like always stick to the system prompt. And then sometimes, and I've seen examples of people doing this online. People will find things they can send to it that'll make it ignore the system prompt. So that's something they've been working on a lot,
Is there a
actually.
name for that? What do they call that?
Not sure.
Jail?
Yeah, jailbreaking.
Jailbreaking.
That's like guardrail,
Yeah.
when you're getting around guardrails.
Yeah, and then there's also prompt injection, that's another form of that, right?
Yeah.
Yeah, I was thinking of a while ago, there was Dan, the do anything now prompt people would give to ChatGPT.
Oh,
So from there, I'm going to go
Can we
to,
make it a,
Come on in.
there's some.
change personality with the,
yeah,
let's make it less friendly, let's make it a, or something fun. Alright.
I cannot spell for some reason. I don't know if that's all right.
That's fine.
But no foul language, please?
Yeah, I know.
Alan wants to be such a family oriented. Anybody under 13 here?
Hey, I have to post this to YouTube.
Yeah, anyone who's-
That's right, yeah.
Yeah.
Oh,
I'm like, you're asking me about that.
We assume these models are friendly and stuff, but they're only friendly because you told them to be
Yeah.
friendly.
Yeah.
They can be whatever
They can be
you decide.
So the system prompt sets the tone for however you want your chatbot or agent to behave, right? It's like a set of instructions about, like, kind of like its soul or its essence.
Yeah.
Would that be considered as guardrail, or is that
Well,
on
there's
top?
there's two types of guardrails. Because a lot of models have them trained built in so that if you ask it something like, how do I make meth? It's gonna be like, okay, no, you can't ask that. And then if you put it in the prompt, you can say like, don't talk about the color blue. And it's not as good, but it will act as a guardrail.
Like a soft guard.
So like an additional,
Yeah, soft guardrail.
So
Softer.
what was the question you asked? Was it just, how are you?
Yeah.
You have the whole thing.
This has gone so far. I remember it was like a year and a half, 2 years ago, you started showing us these things, they barely did anything, and
Yeah,
now it's.
yeah, it's
this
that virtuous
models-
cycle, right? Like as we find new uses that it does okay at, those go into the training data for the next generation of models. Yeah.
And this is local too.
Local to the model.
I don't even have a laptop on this, but
So,
it's better, but it's not as good as his.
so the next thing I'm going to show is that Olama can, depending on the model, for example, Gemma 3 is currently like, I believe the best one with image support. So Olama can actually handle sending images to it. So real quick before I get started showing that, you have to convert it to base 64 so that it can actually send to Olama. So I wrote this little function here.
So base 64 just takes binary data and turns it into text.
Yeah.
So it's sends back and forth in these JSON payloads.
So here's where I define the chat, and I also give it the user message as well. So here I say, you are a vision assistant. You'll receive images and return a haiku about what you see, which I've noticed or up until recently, was a pretty good test to see, can it actually do the right amount of syllables? Since it works in tokens, so it's a little confusing. So here I give it an image I have. Let me see if I can open it. I actually got it from the website.
Hey, our boys.
Oh, the good old.
Yeah.
So I tell it,
So long ago.
so I give it the image and I tell it to just write for this. And then I give that chat to the fake OpenAI. And might take a moment since it's an image. You can see it. Let me see I might count it wrong, but
Robots stand and wait. This will also be curious.
Look,
Oh, it's one off,
Yeah.
depending on how you curious, but close.
yeah, it's usually it actually works. I've gotten
Right,
yes, up
okay.
until now,
Okay, so break this
Smile
down for me.
could be-
What is everything that happened behind the scenes? Like, what did it have to do? Like, okay, because I can't do a haiku. Like, how does that work? What are the steps that it did?
So it's a little weird since it's a language model and this one doesn't actually have like a thinking process similar to like the OpenAI 01 and Qwen 3. So it pretty much, it took the image, turned it into an embedding, and then gave that to the model. And of course, it adds the prompt and says, make a haiku about this. And from there, it just kind of goes.
Okay, so it took in the image. It identified the key features of the image, the people, the robots, the area, the weather, the trees. Like it broke it down into like a description of it. And then it took that description and figured out a haiku from the description of the image.
Yeah.
Holy
That's a
spankies.
better explanation.
No, I mean. Okay.
We can ask a lot of other questions. We say, how many people, what are they wearing?
I
I
know.
don't know, what, whatever was the name of that for.
4 people, 4 robots.
Let's see. I'll change the count. Okay, let's see if it can count. Let me see. what
Your
four-
LLM office.
Let's see, sometimes it's not great.
Wow, I think I got it right. Not for people.
Even broke down the difference.
So it's more than
Yeah.
just an LLM, right? There's some mode, which is
So-
the image processing.
It's a visual VLM.
Yeah.
Typically, so it takes the image, converts it into tokens. All those tokens go up into the model. And then the model finds in, a high dimensional embedding space. And that embedding space is in a place in this high dimensional space where it essentially knows all these aspects.
Right.
So then when you make a language query, how many people, that goes into embedding space, and then they're close enough, it's whatever, there's some sort of, correspondence, and then it sees, oh, there's 4 people. Because it's in a similar place in embedding space. It's hard for
So
humans.
that vision thing is very analytical though. It's creating very specific numbers, words.
Yeah.
It's really very different than an LLM.
But it is a VLM, so it's converting, because the VLM's been trained on millions of images
Yeah.
that have also been converted to embedding space.
Okay.
So Seth, so
Right.
this Gemma 3 understands images and you had this way of doing it. So if I look for models, I look for like vision models, like how do I find models to support that based on what you're showing before?
Alright, so once again, easiest way is to just go to Olama's website and they actually have a
Vision.
way
Oh,
to store.
there we go.
I never
That was
noticed
easy.
that.
I didn't know that either. I really am asking real questions that I don't know the answer to.
You can also type in there, they have a search window here, search models. I type in things there.
And if I
Like-
click on it, you show,
Click on,
like click on Gemma 3,
yeah, it'll show.
is it one of the parameters that it's vision model?
Well, at the top, it just showed that vision right
Is that
there.
models
See
with vision?
See
Oh,
those
vision,
items,
what, okay.
those items underneath, those are the capabilities and the sizes.
Like the 1
Oh,
billion,
text and image, I see.
yeah, the 1
At
billion
the top
is
there, right?
the only one that doesn't support it.
Oh, yeah, text image.
Because, I mean, for robotics, obviously, the images are
Yeah, it's really,
super interesting. It needs LiDAR training.
yeah, but you can merge your LiDAR with that, like what's over here, what's in the upper right of the.
Oh, that's
Huh?
an idea.
Uh-huh.
I need a 3D LiDAR, though, not a 2D.
And then there, can I go to agents? Is there anything
Sure.
else I should add? Alright. Okay, so from there, here's a bit, this is a bit more complicated example. It's, depending how you define complicated. So here I'm using lane graph and lane chain to create an agent that can use tools to solve a problem. So here I've created some tools where basically here you explain what does this do. You need to have what kind of input it is, even though it's still Python. And then you have to tell it what tool, that it is a tool here. And typically you want to do like me, I have a try except in case, let's say the language model gives a non-existent file. And can say, hey, that file does not exist, instead of crashing the whole program. Then here I have a basic calculator. It's, from my experience, the AI doesn't always use it, since for this example, I'm using a thinking model, so it can just do the math itself. But for a lot of models, it's pretty helpful to have that. So I should probably intro on that.
Can you elaborate? You say you use a thinking model. What's the difference between a thinking and non-thinking model?
So a non-thinking model, when you give it a message, it'll just start writing whatever its response is. It doesn't have to think about it, which can save time and tokens, but your responses can be less high quality and it might understand less. Versus a thinking model, which is how like O1 works from OpenAI. A thinking model has a whole thought process. Like, okay, I was asked to do this, so I need to do this by doing this, and then it, like, you give it a math problem and it'll do it like step by step, and then give you a response, and it can check its work and everything.
But you see that in the response, so you'll see, hey, the user just asked me this, I should do this, I should do this, and it'll put it in like a thinking block, right? And then it'll give you the response block after that, so like, it's not an internal thing that's happening, it's like right there on your screen, you're watching the thinking.
Yeah, it's on your screen, but it's demarcated so that you could take it out if you didn't wanna. You know, like if you have a speaking robot, you may not wanna speak the whole thinking process.
Yeah, that's the cool thing.
But it's necessary for it to be as good as it is. It
So-
needs to generate those
Thinking
tokens
Yeah.
to self-reflect. And to sell it, sort of to build up its case with itself, and then it uses that as for the final answer.
Cool thing about thinking models is that specifically the ones that are trained for thinking, they'll usually have a start and end token for the thinking. So if you need a response in a certain format, your thought process won't interfere with that. So you still can use it like a regular model, it'll just be a bit slower. So here I gave it the task, I have a math problem for you stored in mystery.txt. And I tell it to solve it. And from there, I create a list of tools it can use, which I defined earlier up here. And I create an agent with this OLLAMA model, which I didn't know this until pretty recently. Apparently with LangChain, you don't actually have to, or with LangGraph at least, you don't have to define the LLM and then pass that as model. Instead, you can just say OLLAMA : and then however you would type it to OLLAMA, which actually simplifies it a lot. Then I tell it to generate a response, which really what it does is it starts the model and tells it, okay, go do this, and then tell me when you're done, where I then actually print the outputs of it. So if I run that, which I should have probably done a moment ago, it might take a moment.
So this, I haven't seen this also, I know you showed it to me, but I didn't realize these tools are just like 2 lines of code and you created a tool for it. And through reflection and stuff, it knows how the tool is, how to use it, how to call it, just those couple lines.
Yeah,
With
so
with the description.
Yeah.
That the human description is the most important thing for the model to understand.
okay, so you can see here.
Oh, there's your
shows-
thinking.
Yeah, that's what I meant, it's demarcated.
Yeah, so it says, okay, there's a math problem in there, so first I should read the file. So then it calls the read tool with this file. And then the tool responds with what's inside the file. It says Seth is running out of hard drive space. His drive has 8 gigabytes remaining and 997 gigabytes are already used. How big is the hard drive and how much storage would he have if he bought a second? So you can see if I open a scrollable, you can see then it starts thinking, okay, let's see. That info. And then it says, okay, we need to add it, so it then does 997 plus 3 gets 1,000, and then it says, okay, now I need to think if he gets a second one. And then it does the math for that, so it does 1,000 times 2. And then it usually will, with the coin models, they like to go on a while and like double, triple, quadruple check. And then I get the response saying, current drive size 1,000 gigabytes, and after buying a second one, 2,000.
So, I mean, we see that it called your tools, I mean, we must have called your
It called read.
file.
It's
But
right
it did
there.
not call the tool for.
Okay, oh, so we see the tool message for read.
It also might be that I'm using a small model to save time, which from my experience aren't as good at using tools.
Okay, but
It didn't call it
can
calculator.
we tell it like, don't do any math and give it a harder problem, like,
Yeah, in fact,
what's the cube root of the new drive space or something dumb like that?
yeah, if I wanted, I could.
Fourth root of
Do not do
Oh,
math
system.
on your own. Use a calculator.
Oh,
And let's see if it does that right. Oh, we got it. Oh,
all right, so a quick time check, probably last 3 minutes.
okay.
How about a logic problem, like maybe what's the opposite of,
Opposite of what?
like the word, what, like if you ask it, what's the opposite of something, or a logic problem? Can you do that?
Okay, let's see if it used the tool. Let me open scrollable.
You may not have a tool available for that, right?
See.
Yeah, but,
Yes.
but an LLM probably has enough, quotations out there just saying opposite.
Yeah,
there's
there's
probably
Just
no-
in English,
Okay.
maybe a more complicated one, like, you
Yeah.
know, just
One of those actual
family
logic
tree
problems,
type
too.
problem.
Yeah, what you're talking about right now is a whole area called prompt engineering, right?
Uh-huh.
Keeping the agent on rails, giving it the tools and the wherewithal to understand what the tools are for and how to use them. And for goodness sakes, don't guess or hallucinate, right? That's the goal. Because they're fine tuned to be helpful and answer questions. And if they don't know, especially on a smaller model, they tend to guess, which is sometimes kind of fun. But yeah, that whole thing goes into that system prompt and prompt engineering. Keep them on rails,
That's a lot of.
stick in their subject area.
But then there's reasoning, he's getting that, like. if you-
Oh, I see.
If
Okay.
you want to give it a problem that is involves reasoning,
Oh,
then you
okay.
use a reasoning model, ideally.
Yeah, typically down.
Typically down.
Should I go to embeddings or should I just?
I think, you know what? I think we're at a good stopping point this time.
Alright.
Oh, yeah, nice.
Thank you.
Very well.
All
You
right,
did great,
good job.
Seth. All right, any questions for Seth? You're good?
Okay.
Flag this to any practical. Thing practical.
So there's some uses that are pretty, that I can think of off the top of my head. For example, like if you have like an Alexa or something like that, that you want to be a little smarter, be able to do more advanced stuff.
Do personal.
I've used it for anything. I am planning on using it for something I've been doing a little bit of work on, which is kind of like what I said. I wanted to use like a Raspberry Pi. I'm not sure if it'll run the models correctly. I'll have to see, but I want to see if I can do like a basic virtual assistant kind of thing.
Or yeah.
Portable, I like it portable.
One thing I have used it for already is I had a software that would read my emails and then summarize them and write them all into one newsletter of just what's important to me.
Practical.
Nice.
All right, so,
Who do we have next?
10-minute break.
Yeah, let's take a 10-minute break.
There's coffee and donuts in the back.
All right, it is 11 o'clock and we are, back, with our second lecture with, Ethan from Orange County Maker Faire and one of our loved members.
lot of love.
Right, so before we jump into this, I just wanted to touch on something from the last lecture. Using that exact same OLAMA process, we've integrated the same type of thing into the sign up process for Maker Faire. And so, we've got a system running, Gemma 3 on OLAMA. And so the idea here is not everybody's great at writing, especially when they're marketing their maker skills and stuff like that. So when you're setting up your profile, you can type in kind of whatever you want into the box. And then when you hit the enhance button, OLAMA loads up the model. and gives you something that you could replace the text with. That is pre-prompted to give you this marketing spiel for your organization or club. So I just thought that was a kind of a cool little segue into what we just learned.
Did you do that?
Yeah.
Nice.
It was a lot of fun to figure out and figure out how. I love the fact that Olama actually, there's a lot of debate of whether Olama, you know, turning off models over time when you're not using them is a good thing or a bad thing. I love it because it's on my home machine. And so when nobody's prompting it.
It unloads it.
It unloads it for me, it does. Yeah, exactly.
I think I was gonna have you co-locate at your house.
Yeah.
Yeah, really, yeah, that's your own power and.
Yeah. Okay, back to what we were going to do. All right, so I'm actually gonna, let's go and do. Okay, so today we're gonna talk about motors and some power. We're gonna start off with just motors and kind of go through the different types. We've, over the last few sessions, we've been kind of utilizing a few of them, but we haven't really dove into the different types of why would you use them and what they're good for and stuff like that. So today we're gonna try to break that down a little bit. So when let's start off with the most basic, let's start off with just DC motors. What are DC motors? You know, there are motors that continuously spin. You can control them via PWM or voltage, so turning power on and off. Commonly used for wheels and things that need to just continuously move. Those motors, we've seen them in the robots that we've used or that we started building it in session 1. You can see a picture of it, the TT motor. It's just a very simple, very lightweight motor that are like $1 a piece. So great to play around with and figure out, you know, does the motion work for you? You can control it with the simple motor controller, an H bridge. Turning power on and off. You want it to go forward, you send power over one of the 2 wires. If you want it to go backwards, you send it over the other way. So you're just switching power direction, reversing the polarity of the motor. These are very common all over the place, very easy to use. We've used it in our code in session 1 to make the robot go forward, backwards, turn left, turn right, and just get it to slowly move around. The second type that we're going to talk about is servo motors. Servo motors are a little bit fancier. They still have a base of a DC motor in them. They are geared, and they also have position sensing in them, so that they are a lot more precise. So they are really used a lot more for go to an angle and stop. So if you need something a little bit more precise, like picking up things with a hand or manipulating something, servos are give you a lot more control over where they're going to move. You can tell them to immediately go to one position, and they will do that every time. Depending on the size of the servo, you're going to get a lot more or less precision out of them. Are they metal geared? Or are they plastic geared? You know, there's a lot of slop in there. So while it says it'll go to 180 degrees every single time, plus or minus. There is a special type of servo gear called a continuous rotation servo, which acts a lot like the standard DC motor, where it will go round and round and round, but still gives you that ability to define a location. So it's kind of a hybrid between the 2 of just continuous rotation and precision angles. Unlike the DC motor, there is a third wire going into these motors that is the signal wire, which is how you control where you want to go. You're going to tell it the precision position to go to. Let's see. I think that's all we need to cover here. We used one of these in the second session when we started looking at sensing the world, being able to move the sensor around to determine direction. We wanted to make sure we could look left, look right, every time the same way. All right, third type of motor, brushless motors. Brushless motors are very similar to standard brushed DC motors. But the difference is there is no connection between the shaft and the outside of the motor. They don't actually touch. With brushed motors, they will eventually wear down. They will slowly lose accuracy, lose capability. They will continue to run, but they will be less effective. With brushless, they're longer lasting because there is no friction in the moving components. It's all done with magnetism. It is very similar to the servo in that you can control it through the ECS with a signal on rotation and movement. Let's see, they have very high torque at very high speeds, which is, I believe, a little bit different. Does anybody know? Is that does the standard DC motor have less when it gets higher speed? It does, right?
Yeah, I think I just read this article. It said these have higher torque at low speed as well. And
Probably.
the DC motors don't have that.
Yeah, definitely that's the case for steppers, which is a specific, almost like a flavor of the LVC, right? Phases. That makes sense.
Yeah, there's a great article in Make Magazine. your the bigger organization in the skill building back of the thing. It talks about.
You mentioned there's two really nice benefits. Well, one is it's really efficient because it can continuously modify the electric wave to make a perfect like sine wave. And so it like runs less battery. And the second one is because you don't have the brushes that like arc and stuff.
Right.
You don't have that electrical noise wrecking everything else on your robot. So these things are a lot better for these noise issues.
So that's EM, electromagnetic interference.
Yeah.
All that.
That's a good. Yes, we will. All right, the next motor type is linear actuators. Oh, there. Okay, so linear actuators. I put this in here because it gives us another look at another use case. So at its heart, it still has typically is just a DC motor that is got some sort of gearing, but it translates that into linear motion and gives you strength with ball movement. So it converts that rotational movement into the straight line linear movement. A lot of these are great for being used in arm and extensions and holding things up and holding, closing things. And there's a couple different ways that you can accomplish this. Some of them is you can use the electric, pneumatic, and hydraulic type of motion or motion. Force to produce that linear motion. And you can accomplish that in a lot of different ways. So there's some control options on how you can use those. A lot of times they have a limit switch so that they stop moving once they reach their extension. And that way you're not pushing that rod outside of its capabilities. Okay, stepper motors. Stepper motors, I left this to last because we're gonna actually play with one today. Stepper motors give you precise movement, very much like a servo. They do give you continuous rotation like a DC motor. And it is very similar to brushed motors in that you're using magnetism to rotate them into precise movements. So you can get very, very accurate movement with these. It's based on turning magnets on and off, which we'll see in a little bit. And it's a sequence of pulses. So I'm sure everybody has at least seen one of these. If you have a 3D printer, you've used one of these, and whether you know it or not. So 3D printers and other CNC style machines use stepper motors to do their movement, and that's how they become very accurate in reproducing what you've told them to reproduce. They're very high precision in that they'll have a certain amount of steps per rotation. So, for example, the 2048 positions to create a 360-degree movement allows you a lot of steps to find the exact angle. Some of them have twice that or more, and you can kind of control how you define what those steps are. So you can make one of these motors more or less accurate a little bit by adjusting those in your code, and which we'll see. Okay, so how do they actually work? So there is a set of magnets around the outside, and then the barrel is magnetized as well. And so by turning on the magnets on and off, you can produce this rotation. So if you wanted to go to a very specific location, you're going to turn on sets of magnets to get that the shaft turning. So there's multiple coils along the outside arranged around the rotor. Let's see. There's no position feedback, so that's why your 3D printers are always homing themselves so that you can get to a known position, because they don't know. There are some that do, so there is a caveat to that, but the basic stepper motor doesn't know where it is when it first turns on. And so finding that home position for your 3D printers is the reason why it can do that, because then it knows where 0, 0 is. And when you tell it move 6 steps, it knows it's going to be at the same location every time. And counting those 6 steps, it just, again, goes down to we're counting pulses on the coils, turning them on and off. Okay, so today, for the stepper motor, we're going to use a controller, which the the stepper motors require to be controlled by, Raspberry Pi. We're going to see first, we're going to do it with a simple version of the code to kind of get our feet wet and understand it, and then we'll look at a slightly more complex version and how they differ. All right, let's Yeah. Oh, no. There we go. Hopefully you can see this.
Oh,
Can we full screen?
yeah, sorry about that. Let me. There we go.
Okay, so let's go over the, what we have hardware wise here, and then we'll kind of jump into the code. So we have a Raspberry Pi Pico, and it is wired up to a motor controller. Motor controller has 4 signal wires going into it. That is being powered. It's backwards on my screen. There you go. Okay, so we've got a buck converter that is just pulling 12 volts from the wall, dumbing it down to 5 volts. See in the light, but it says 502 on there. That's powering the motor controller, which has a driver on there. And then we've got just a very simple stepper motor, and I just put a little flag on there so we can see the direction as it moves.
What is that little gray thing that was on the side? Little gray box?
This,
Yeah,
this is just a Wago wire nut.
oh,
It's just easy to put wires together. You probably seen twist ones that use an electrical. This is just they've got 2 little flaps on them. So you pull that up and you can put the wire in, then it clamps down on the wire. Okay. Let's go back to there. Okay, so this is our simple version of the code. So we know we have a Raspberry Pi Pico. We defined our 4 pins. Done this every time through this series. So I'm not going to touch too deeply into that. But the next thing is the sequence. The sequence is defining the pattern of coils being turned on and off. And so you can kind of see, regardless of whether you understand the numbers that are going in here, the important thing is you can kind of see a pattern of ones are moving across the array. And that's what's defining our process of turning the power on and off. Then we're defining a very simple function that's just going to step the motor. We're going to define a delay, so how long between steps, and then how many steps should we take. And then our loop just goes through and it's going to break down each step. So every time it goes through this loop, it's going to tick off one of the steps that we asked for. And then inside that, it is turning the sequence of coils on and off using our sequence up here until we reach the amount of steps that we want. And then we're just going to, we're going to call that function and actually perform these steps. Is there anything in this that anybody would like more detail on? Okay. Then let's go back to the video and we will see this in action.
First. We're switching back over to the.
Very concise code, by the way.
Ah,
Congratulations on that.
Ethan, I think
Oh,
you might need to stop
yeah, yeah.
sharing. There you go.
Okay. Let me run now.
Oh, the thing.
Yeah, I just.
Drag that thing
slide it
over.
over. There. it is.
All right, and so
Hey.
so we told it to make 512. Wow, this video is very choppy.
Is that the video or is it really?
It's a video.
Okay, it's smooth on your side.
Yeah,
Okay.
yeah. So the video made it look a lot choppier than it actually is in person. For anybody who's here, can see slowly moving.
Very smooth.
Oh, I'm not? Oh.
There you go.
All right. Okay, so we know it works now. We've gone through some very simple code that
Sure.
cycled a stepper motor. What was that?
We're gonna share.
Yeah, I'm gonna share it. All right, so now let's look at a little bit more advanced version of this. So we're actually going to define a class. This is a Python concept that I'm not going to dive too deeply into. It's all about programming, so I'm going to somewhat stay away from why we're doing this and all that. So very similar to our very simple code. We are defining what does it take to run this motor, or any stepper motor consistently, and give us some different options to run this motor. So I'm going to scroll down a little bit. So our step until is very similar to the code function that we ran just a minute ago. We want to go this many steps. We want to go forward. We've also defined step until an angle. So we want to define an angle to go to and let it figure out how many steps it needs to get there. Step degrees. I don't remember what this is again for. Okay, so ignore the current position, start from 0. Okay, so this one is, I believe, how many steps is it going to take to get to a specific degree angle. And then at the very bottom, we have two classes that are defining two different sequences. And so I talked about in the last one, our states pattern, or our sequence pattern of how turning on and off the coils will function as movement. So in our last one, if we remind ourselves, we had a nice big long list with ones cascading. In here, we're defining two different step patterns for this motor. One becomes a lot more accurate than the other because you can stop it sooner with more steps per rotation. So if you want it to be more accurate, then you want more states. So with the full step motor, you're moving one full segment per sequence. With the half step motor, you're moving half that distance with the sequence. Okay, so let's go to a class or a program that we've written to use that stepper motor. So loading both of those files. Here on Thonny, we can see, well, I can see, maybe you can. loaded on the Raspberry Pi, we have the stepper class, and then we have our program that we're about to run. In this program, again, we're defining our pins. We're making sure that we are in a zero state for our motor. And then we're just going to continuously loop in sets of movements based on the classes that we called. So we're going to step until angle 2. We're going to take 500 steps. We're going to take minus 500 steps, so run backwards. We're going to step until we hit 1,000 steps. So this go to a specific position. And then the next one is we're going to a specific position, but we are going backwards because we're changing the direction. And then we're going to just move until a 90-degree angle.
You're doing, when you say counterclockwise and then direction -1, is that?
So, yeah.
Is the same thing, is direction related to the counter or clockwise?
Yeah, so the different functions have different variables. So one of them, if it gets a negative value, it's going to basically go through and set direction to.
Okay, so it's an either or.
Yeah, so you can see up until. Here we go.
Less than 0.
So it's going to use direction of 1, go forward, unless, yes,
So that's if direction is none.
Yeah.
Yeah, then it does it for you.
right,
And if you put it in, it's explicit. So it's just flexibility
Yeah,
of the
exactly.
programming interface. That's cool.
Okay, so if we come back over here and run these programs, like I said, we're gonna go to 2, 500, -500, 1,000, -2,000 technically, and then 90-degree.
Oh, so this is all different ways to do this. Same
Ethan,
thing.
can you stop sharing so that I'll zoom?
Yeah, sorry.
There you go.
Why?
Oh, well, I can do it here, but then everyone else locked in.
Oh. Or he's forced.
Yeah.
There we go. See it moving back and forth, different directions. And at different distances. And it'll just continuously do this pattern over and over and over.
Cool.
Huge. Okay, so if we look back at our code, we have a while equals true. That just means do it forever. Don't ever stop. Unless you have a keyboard interrupt, which most programs, most OSs have. So hitting Control-C will trigger the interrupt and make it stop doing its loop forever. Okay, so each one of these motor types has different purposes. And so choosing the right motor for the right job is kind of important. A motor for the sake of motor isn't always the right answer. So picking the right motor, like I said, for what you want to do is important. Okay, so let's go ahead and move on to power.
Just real quick,
Yeah.
the motor and the set you just showed us. just roughly the prices of that kind of thing and the kind of torque you get out of it?
Oh, that's a good point to bring up. Okay, so this setup, probably dollars. In the motor, this little tiny motor.
That forever.
I did say forever, and it was running forever.
Yeah.
So this little stepper motor, I would bet $1.
Yeah.
The driver, probably another $1. So I mean, we're not talking about big components. This motor is not, I wouldn't say super strong. It makes a good clock. It would make, it could probably do very small robotics type of thing. But stepper motors come in all sizes. You know, the ones on your 3D printer are NEMA 17s. And that's how many coils are inside the motor. That number represents that. And they're a lot stronger. If you've ever tried to wrestle your 3D printer or try to take a print off while it's in your way, it'll probably break your hand. When you start getting into the CNCs, you're looking at, you know, NEMA 23s, they're usually a lot bigger. Start looking at other types of applications, you can get some pretty big linear motors. With servos, if we go back to the servos section, servos come in all different sizes as well. And they always have they always have a weight rating on them. So you'll see 60 kilograms, 30 kilograms, or less. The MG90s, which is probably that little tiny one at the very end, those are 9 grams. But all of these weight ratings are like millimeters off the shaft. That's what they're rated for. As you get further away from that shaft, that power decreases, I believe on an exponential scale. So once you get about a foot away, you're no longer at whatever that rating is. You are some fraction of that power. So the bigger item, or the bigger that the item has, the bigger the item at the end of the arm on your servo motor, the bigger the servo needs to be. So don't think I got a 60 kilograms so I can lift 60 kilograms of weight. It's just at the shaft, that's how much power it can produce, and then it'll die out as you get further away from that shaft.
Right, so that's because typically they'll express it in a weight and a distance, right? Like
Yes.
foot pounds or kilograms,
Yeah.
something else, right?
Yeah.
Okay.
One question on the servos, on the stepper motors. So when people want to go back to a home position, do most people, I guess, do a hard stop where they go to they push it all the way to the very beginning, or do they use optics as their stopping point?
So the basic stepper motors are usually using some outside sensor to determine what they consider zero. So like on your 3D printers, often they have limit switches or some other force mechanism that determine I'm at a limit. Then the logic on your code says this is 0. Now from this point, turn to go a certain distance. So the motor doesn't ever sense. There are some other sensor outside of the motor that's going to determine 0.
Yes.
The other question, do you have to ramp up with these to make it dependable? I don't know what, I've seen it somewhere before where they lose their position because of the torque on them or something like that, so they'll forget where they're at.
So typically the loss of memory usually has to do with an external component. So like if it's driving a belt, the belt slips. And so now the key on the rotation is off. So it thinks it ran 2, but the belt slipped and you actually ran 3.
I think you do have to have, like, if you want to go very fast, I think you have to have an acceleration profile to get to that speed, or you will lose stuff.
Right.
One more thing, on a stepper motor, the holding torque, if it's not rotating, is quite large. But the running torque, when it's rotating, is substantially less torque. So one of the effects that has, if you really get fairly fast, it's far more likely to lose steps.
Okay, so that's- Okay. Okay. Nice. Those. Very good at holding position.
They're good at holding position, but if it's gonna be a battery operated robot, you could run the battery dead and that motor is actually not rotating at all. Because to have it stay where it's currently angularly rotated to when there's any kind of torque on it, you have to keep the amperage through those windings all the time.
Yeah.
So that's one disadvantage of this stuff.
Oh, usually like on 3D printers, you can set holding the average and usually you specify much lower than amps that you are running steadily.
Well,
Well,
usually a 3D printer is connected to your house supply.
yes,
Or,
yes, but it will
robot
help, it helps
battery.
to lower that power input.
Yeah, Mike, sorry.
Oh,
Well, I had a question. Are you gonna talk about half stepping? And in particular, I'm wondering, I think you can half step in order to increase accuracy, but does that also decrease the torque? Are you gonna talk about that at all?
I hadn't planned on it. We kind of touched on it in the code.
Yes,
But I didn't
had
go
a
into
half
detail.
stepper function. I think sometimes on the motor controller with the jumper or something, you can set it up so that it can do half stepping,
Micro steps.
so micro stepping.
Yeah, so, I don't know how, I don't know how that, I'm not an expert at that part, so I don't
Right,
know.
neither
enough
am
to
I.
know.
That's why I asked.
Yeah. I know the possibility and the capability. I don't know what that affects. Anything else before we move on to the power section? All right, so power section, let's see here. Okay, so when you're dealing with robots, there's kind of we're kind of talking about two different segments that power is required. One is the brains, the logic, boards. The other is motors, and those are like the muscles and movement items for your robot. Usually they require very different power requirements. So it makes it challenging when you're trying to balance low wattage or low voltage precision thinking with high voltage movement for muscle. Despite potentially using the same power source for both of those items, you want to make sure that even though they have different power requirements, they have a common ground. You can use things like capacitors to help smooth out those power irregularities in your robot. To make sure that as the motors draw power, you're not getting spikeages in the logic aspects of it. And the most important thing is with every component on your robot, you just really want to know what your components need. That way you can go into it trying to provide the proper power for those items. Okay, so some common symptoms that you have some bad power. Your motors are randomly twitching. You have sensors giving you bad readings. You have hum in your motors. And the logic boards reset. You know, these are all kind of some of the common symptoms that you probably have a power issue somewhere that you need to start tracking down before you blow something up, release the magic smoke, make your robot have a bad day. All right, so adjusting power. So when you have a power source, so as we saw in our example earlier, we had a 12-volt power supply from the wall coming in, but the board that we wanted to use with the motor, we wanted it to come down to 5 volts, so we needed to step that power down. In the same way, you can also step power up if you have a certain voltage coming in, but you need more. And we'll kind of quickly discuss the differences and some of the drawbacks for doing so. So, you know, for example, with boost converters to step up the voltage, while you can get more voltage for your component out of smaller batteries, you're going to drain those batteries a lot faster. So yes, you can get consistent power to them, but for a much, much shorter time than what you probably expected. Then in the same way, buck converters drop that power down, and there's a couple different ways to do that. You can do a buck converter, or you can do a regulator. Basically, those often release a lot of that excess power as heat or other ways to reduce that voltage down for the robot. Okay, so what is the difference when we're stepping them down between buck converters and regulators? So the efficiency of a buck converter is very high. You're not usually losing a lot to heat. And it uses capacitors and other components to help reduce that power efficiently so that you can draw it down to a voltage that you need. The regulators are typically a lot simpler devices. So if we go back here, you can see a regulator versus a buck converter. So this is very easy to very small, drop it on a board somewhere, and it will do one thing only. And the metal piece at the top, I believe, is usually a heat sink to help release that heat during the voltage drop. The buck converter, as you can see, there's a lot more components to it. This is the one that's shown here, actually happens to be a variable one, which is what I have here, and we'll do an example of how do you use that to adjust that power. The buck converters are, when I say that the regulators are cheap, I'm not saying the buck converters aren't cheap, but they're just definitely not as cheap as the regulators. That's the buck converter that I have here that allows you to adjust power. Again, we're talking about $1 or $2, not a lot for a buck converter. But when we're talking about the regulators, we're probably talking about pennies, not dollars. The regulators are awesome for like actually I have a very small regulator that I use for my Raspberry Pi Pico on a lot of my robots because it's great at taking voltage down to 3.3 volts. I mean, that's the only voltage it will go to, but it has a very small milliamp limit on it, where the buck converters often have a lot more. So they, you know, for a full Raspberry Pi, I'd probably use buck converter instead of a regulator. For motors, buck converters are great. Anything that has a lot more high current, I'd probably go with buck converters in general. All right, so let's let's look at how, got only a couple minutes left. Let's look at how we control the buck converter to drop the 12 volt down to the 5 volt. So they're actually very, very simple devices. They have 2 wires coming in, they have 2 wires going out. And so in this example, or of the example picture, you can see the 2 blue terminals at each end. They have little screws in them, so you can put positive, negative wires in both sides. This one happens to have a screen and a button. And then this little blue component up here has a little screw in it as well. And this is how we're going to adjust voltage. So let's switch back over to sharing screen or sharing video. Yeah, my phone is not cooperating. Slightly different. That works. Okay, so we have our buck converter here. You can see we have a positive, negative coming in. We have a positive, negative going out. This is connected to a 12 volt wall adapter. And then this is going to my robot. I have 12 volts coming in. I want 5 volts on the going out. Right now it's currently set at 5 volts. And if I press the button, it shows me, you can kind of see an LED right here. And when I press it again, it switches to the other LED. So that's telling me this is input voltage and output voltage. And so when I select the output voltage, right now you can see it says 5.0. But if I take my screwdriver and I start turning this, you can see the numbers changing on the screen. So I can dial in how much power I want to come out of this buck converter to power my device. So very simple device to use, very powerful, very useful. Any questions about this?
What's the maximum amps watts for this one, that one using right now?
The top of my head, I don't remember.
Might be clear at the bottom.
It is not. Let's look it up real quick.
Yeah, because these come in all kinds of shapes and sizes, right?
They do.
And power ratings.
So here's one and 2 amp. 1.25 volt all the way up to 37 volt, adjustable. With a 4 to 40 coming in.
We still.
We're watching your email.
Oh. They're getting.
Hey, you paid for parking, good job, you.
There's been times I haven't, so I'm glad to see. All right, so here's one.
A comment, I think in FPV, they call these things BECs or UVECs, battery
Yes.
eliminator circuits. And sometimes they come really tiny. 'cause
They do.
These micro FPVs sometimes need really tiny light components.
The RC world.
In the RC
Yeah.
world, you use these a lot.
Yeah,
They can come very small. You have 3D printed items, they do sometimes get hot.
Yeah, they get warm.
So be aware of that. The nice thing about those buck converters, is they're a lot bigger, so they don't get quite as hot. And as these do, as you can see, these are very small.
But same technology, I think, right?
Yeah. And pretty much same technology. These are usually either often similar to regulators in that they usually are set to one voltage output level. Some of them have, like this one has, you can see this little jumper at the end, and it will go from 5 volt to 6 volt. Those are your two options. There isn't a very big variability in them.
I think a lot of these work on the principle of you have a high frequency primary side of a transformer and it comes out the secondary and they rectify it. I think
They don't use transformers at all.
they don't.
No, they just use MOSFETs, switching on and off, maybe conductor. Diodes. Like they're not galvanic and isolated at all. So they share ground with everything.
You can get smaller buck converters without the screen and buttons, which does shrink the size a little bit. Without the big terminals also. But with this, you need to you plug in your power, and then you need something sensing the power on the other side while you adjust it, so that you know what the output voltage is. It doesn't show you on a nice screen.
Why, once you see smokes and.
I mean, you could use the magic mode.
Bring it back a little bit.
And they call it smoke test, right?
But you can see that this was $12 for 10 of them. So I mean,
Crazy.
Oh. All right, Ethan, time check?
yep. So I'm good.
That's cool.
That's the end of my presentation, unless anybody has any questions. Yes.
How does mechanically turning the screw change the voltage?
It's a resistor, it's a variable resistor. So sometimes they have like one turn, so it's not very accurate. Sometimes you get 5, 10, 20 turns. So it's basically just changing the feedback to the controller.
Any other questions?
Oh, man, this is great. Thank you so much.
All right, so again, if anybody has show and tell, let me know and I'll add you to the list.
We're live.
Meeting is being recorded.
All right, we're back. This is where we have any announcements or anything else you guys want to bring up. This is the time. Anybody? Announcements? All right, so let's get back to our show and tell. Or can you
Just,
remove the
you can just unjoin audio, you'll be good. All right, thank you.
first show and tell? Alan?
Okay, all right, so, oh, I'm live. Okay, let's do this. It's me. All right, so a couple of updates on Alfie. Alfie, I got a little bit busy, so I haven't fully reassembled him yet, but I've got a bag of stuff and there's a couple of things I wanted to get in front of you. I'll just pass them around. So first off, this was Alfie's previous frame. It's a Radsta Rock 5C with a passive heatsink, 60 gigabytes of RAM, 64 gigabytes eMMC, and a 512 gigabyte SD card. And this worked great. But I got hungry for being able to run large language models faster. So also in here is my Jetson Orin Nano NX 16 gigabyte with a custom Seed Studio carrier board and set up to fit exactly in the same volume that the previous SBC and buck down converter for power delivery fit inside the case. So let me go ahead and pass these two around. And while that's being passed around, and open up the cards as well. And also, part of the bag of parts, there's the 2 fans that blow front to back to keep everything inside electronics bay cool. And the 2 cut down wave share boards that provide connectivity between all the peripherals and the main board. So we'll pass that around. And let me go ahead and share my screen. Just a moment.
This is the, right. Right, so this is the. Right, similar to like what I have, so 16 weird. Oh, yeah.
Okay, all right, let me move some things around. All right, so a quick tour of what I've done to my poor Alfie. I was so proud. He was online and assembled for 2 whole months. So here's the current state of the electronics bay. Whole bunch of wires. I did shorten a whole bunch of them, but now I've got 1.5 foot of USB 3 cable. I have to pull it around somewhere. Here he is on the bench before I put the thing back on. Here's his new base. So the previous base is in that box, just to give you. Oh, sorry. Let's go ahead and pass that around too. So it's a carbon fiber PET-G with some Dremel additions underneath, as I forgot stuff in the previous design. Most of the wiring harness goes through the front channels of that aluminum extrusion, that 1/3 of a Delta printer. And so it's a view of the inside. So anyways, not a lot of space, very easy to fill it. Ignore the socks and flip-flops. All right. So one of the big things about moving to the Jetson is you get accelerated large language models. Now on the rock chip board with a 600 million, or sorry, 0.6 billion parameter model, I could get about 18 tokens a second. However, as Zeth rightly pointed out, and I completely glossed over until I started trying to use it, 600 million parameter models are kind of useless. They don't do much. So I think where I'm landing is on the 4 billion parameter model. I have enough space so I can load up the speech model, the text to speech, the speech recognition model, vision module, and the large language model in 16 gigabytes. I should still get more than 20 tokens per second, which I think is acceptable. I do want to toy with that 1.7 billion parameter variant just to see, once I decide to figure out what I want it to do, to do something, if it'll work. But probably I'll just end up here. The 8 billion just takes up too much space. The last thing is that probably a lot of you know that I am a big Fusion evangelist, designing components in a 3D modeling software brings me joy. I have a subscription as a result. I tend to try to pay for the things that are super important to me. But I don't use Windows or Macs, and those are the only 2 operating systems that are officially supported. And while I've worn my badge of honor about figuring out how to get Fusion 360 to run under Linux, it is a royal pain, and it bugs me to no end trying to keep it working. So I blame Brian for this. Brian got into the 3D modeling scene with Onshape. And I decided to dip my toes back into it, and I think this is where I'm going to stay.
It was boomerang. Who recommended it to me?
That's fair. So Onshape is completely online through your web browser. It runs super fast. You can run it on any operating system. You can run it on your phone. You can run iPads, Android tablets, and it has pretty much all the same features. And as long as you're not using it commercially, and as long as you don't have a requirement to keep your designs private, it's a really good fit. In earlier years, I used to really care about, oh, this is a cool design, I'm going to make money. And the truth is, nothing I do is that interesting or important. And I'm a lot more. I softened up a lot about just leaving things online. So I'm gonna probably spend as much time as I can in Onshape over the next year, and I'll probably keep my subscription for another year or two, but I think the writing's on the wall. I think this is gonna be my new home for development for a little while. I know it's a long time.
Yeah,
coming.
so it's a big,
The FRC team I mentored, there are a bunch of students who are like, we have to move to Onshape. It has some extra plugins that make a lot of sense.
Yeah.
There's been a big debate about moving
Yeah.
Fusion.
I've been impressed by it.
Really, you like it? Because
Yeah, it's really great. There's a little bit, if you're pretty good at Fusion, there's only a couple of things they do differently that you just have to figure out. And if you're gonna take this all the way through to a robot, there's built-in plugins to move your fully articulated robot into NVIDIA Omniverse for simulation and other stuff.
Oh.
And if you're doing the robot route, they do it all through Erdif, so common standard, not as awesome, it still works. But there's an exporter to export your robot to Erdif with all of your center of mass, center of gravity, articulations and limits that makes that path easier for the robot and Mujuko, I think. So, yeah, so I'll have them assembled very, very shortly. I'll continue kind of playing with these components. And then for the next step for me, I'm talking about putting these things together to do something interesting. But there's a whole other area of what Jim showed me, VLAs, vision language action models. So the robot has something for that. Groot is a version of that. And that is a whole different coordination behavior thing. So, and that's what I need moved to. Because again, as for our new folks in the audience, at its best, my poor little Alfie will be about as helpful as a 5-year-old, right? So not super helpful. We're setting a really low bar. It's taking advantage of the same advances in humanoid robotics that are happening on the commercial side right now. So as those become available, I've got my low cost Temu or Temu humanoid here to work with them. And my first thing I'm going to do is to train an RL policy that allows it to give high fives. And so when I've got everything set up, I'm going to bring Alfie and I'm going to get you all in a line and I'm going to record about 20 interactions. And that'll form the basis of real world data to then use another NVIDIA tool that can extrapolate that into 10 or 20,000 additional synthesized interactions that then go into training an RL model for the express purpose of helping me understand how to do this with a side effect of Alfie knowing to high five you without programming the motion specifically. So that's the update. I'll keep it posted over the next couple of months. Hopefully that's on the horizon. All right, thanks.
Thank you, Alan. Wow. All right, I think, let's see who's next. Let's see, you ready?
Kind of, I haven't prepared form to meet streamers. And anyone?
I think that the stream, does anyone want to do it here?
Yeah. So, for a couple weeks, I've been working on this RC car called Death Racer. So it's somewhat popular within 3D printing community. It got popular because of what's his name, Sam Prentice. So I don't think he designed this model, but he organizes events like RC battles. As the idea behind it, there are three I think more different models. One like this with wheels that can move from side to side. One which looks like a tank. Maybe two models. Well, I picked this one.
So I'll post the link. What is it called? I'll find it now.
So it has 4 wheels.
Yeah, there's not really a.
Omniverse.
Oh, okay.
Unfortunately, to get the
So
model.
it's somewhat open source. They advertise it as open source. You can buy a kit with hardware parts, not for this model, different one, as I realized later. You can pay $1 to get access to Patreon, and there you can download all STL files to 3D print, Fusion file to modify if you want. There is a pretty detailed guide how to follow, how to assemble everything. So I bought a kit. It's for different models, so I didn't use most of the parts from that kit, so I had to pay extra. 400 or so to get extra motors and things. But basically the idea is that you build this RC, there is a small driver here with a switch instead of neck, I would say, and there is a headset on top of the switch. The goal is with this weapon behind car. So it's driven by motor and it will spin eventually. So with this weapon, you are supposed to detach head of a driver so far, like opponent cars. So once that head is off, RC is turns off, and you basically win. I think they started to do different kind of competitions. You have to be at top of the hill, like you stay to be alive at the end of match. They do some kind of capture the flag. I don't know how exactly they work, but I will be bringing this RC to Rise 3D printing events, like 3D print Utopia, RepApp festivals, and hopefully I will compete and maybe win some prizes. So this will be powered by 12 volts. I was going to assemble it yesterday and to make it work, but I realized that there are different types of XT connectors. So those used in a kid's XT30 battery XT60, so I had to get XT61 to connect battery. So they in a bomb they link those motor drivers from Go Builder company. I think they sell also kind of kits and all components to build RC car easily.
Servo City, yeah, it's the same company.
Okay, I never use them, and I don't know if there are cheaper alternatives, maybe. But so I got 5 of those, 4 for to drive to move car forward, and there is 1 for to spin a weapon once it will be connected with the valve. Also, from the Go Builder, I bought a power distribution board, and this helps to convert transmitted values to those that work for the zombie wheels. I don't know how exactly it works, what's inside. I assume there is some kind of microcontroller. I should probably open it up too, because I'm curious.
Don't let out the smoke.
Yeah, and just RC receiver, yeah, wireless receiver. And that's pretty much it. Since I have a model, I modify some parts that I prefer to look differently. Like I didn't like how wheels are built, so I modified parts a bit to have heat set inserts instead of screwing screws into plastic. Yeah, it will take me a couple of weeks more, and then I hope we'll have a small test flight with Ethan, with Dom, and maybe someone else is 3D printing gloves. Yeah.
Yeah, we should take them outside and see what they do.
Yeah, well, once it works, maybe next time I'll bring it.
Okay.
So when it works.
Right on.
Oh, thank you.
Looking good, thank
It's
you.
basically Rock'em Sock'em robots.
Oh, really? Yeah, and those are kind of safe. So you can build RC cars that need to be enclosed in a cage, so it's safe because they have metal weapons and spinning rotors and whatnot. This one is kind of safe. They usually run in the parking lot. They haven't killed anyone so far.
It is very much meant to be non-destructive, and the point of knocking the head off is switches the rocker switch to just turn off the robot. So.
Oh,
that's
okay.
the
So it's like, just like Rock'em Sock'em?
Yeah.
Where that you're
Knock the head
dating,
off.
where old people remember that.
All right, thank you, Jose.
Vasily, thank you.
Next up is Brian.
Okay, that's gonna help me out. This is kind of a tool update, so we got 3D printer loves it so much, so the next step in the evolution, we get it. Oh, you get it? Anyways, we'll get a picture of it. It's CNC. So CNC is either a mill or you can call it a router. It's got a spinning little drill bit thing that can drill in sideways and up and down and everything.
Yeah, you're moving fast into the tools.
Yeah, it's got I can tell you it's a bigger learning curve than the 3D printer. And then I tried using FreeCAD and it was really janky. Like, so I got this print here that I did. I did this with FreeCAD and it took me a while.
But it works.
With the other software, I made my own, but this one's better. I took a picture of the Space Needle, converted it into a 3D relief using some bamboo software, and then printed this out on a piece of wood. I figured out how to drill holes. So that's cribbage. So you just use a regular drill bit for this one and drill a bunch of holes. And then another one here, instead of using a straight down flat bit, I use a 90-degree V bit, which gives you like kind of finer control. You get really nice things. So just a little bit about the wood. In my backyard, I've taken apart pallets and like let them rot in my backyard. So they're old and ugly and twisted. So I put this old, ugly, twisted wood into the CNC. I mill it flat, flip it over, I mill it flat, and then I put really nice wood out of it.
Oh my gosh.
So yeah, this used to be really ugly and warped and everything now. This side I oiled to try to make it nice, but it's not so nice. But yeah, that's.
But the palette, yeah, leaving it out gives it that weathered look too, right? At least I'm.
Well, I mean, it does on the outside, but like, it turns out your palette is nice inside because it only goes so deep. And so you have like this nice wood.
But you're just using that because it's convenient, because you have.
I had in the backyard and I sawed a little chunk of it off and milled it flat. And so now you'll see it's rough on the sides. You can see what the palette looks like on the outside. I'll pass these around. So but this is cool. This took about an hour, but which is a long time, but.
What size was the bit? Like there's different bits.
I think, so it's kind of a tapered bit. And I think it's got a 16th ball at the end. So at the very end, there's like a 16th of an inch resolution that you're working with.
Okay.
And for something like this, you run it through like many passes. So it's going up and down and up and down and up and down. It's very loud. You have to hook up a vacuum cleaner or else you get dust everywhere and it makes you cough and everything.
So does it like take off the top? Does it render layer by layer, but in reverse, or does it start with the corner and go like, what is the
so like? For this one, I had two steps. I had a clearing step, so I used a big fat bit and get it down close
Your roughing pass.
Close to the roughing pass, and then use this 16th ball, which is only taking off maybe a few millimeters of material.
Okay.
But like I said, it's taking a long time. Yeah, so that one I think was because that was a photograph that I.
So we're sharing right now.
Yeah,
so-
stop sharing stuff.
But do you have to put in those instructions for those passes, or does the software do that for you?
The software does that. So you take a 3D model, you put it on there, and you give it instructions about what tool you're using and everything, and it calculates what's called a tool path, which is up and down and 3 dimensions to make that.
You have to tell it the tool you want.
Yeah, and I started making my own, and I was able to do that on my own software, but not as good. I was able to make the Space Needle, but it's too involved, so I just bought some software.
Oh, yeah.
You could probably make some pretty cool litho paints with that.
Yes, yeah.
Yeah, better than a 3D printer.
Yeah, a wood litho paint, wow.
Yes. And I thought I should just decide when to I just took a photo and turned it into that.
Yeah, look at the really fun.
Or did you end up settling on?
V-Carve. I think it was I got the desktop version. It was under $400.
Oh, it's not cheap.
It's not cheap, but there's way more expensive software.
You got the pro version.
But that's not
more than
most of us. Pro version is like software. It's not like back in the day.
I'm at 320 a year for Fusion. So, but yeah, but like I used to.
Oh, you got the pro version.
I did.
But I wanted to use, let me just show it. I wanted to use Onshape
Yeah.
But theirs is like $1,600 a year for the cam capability, so like, that is one gap for Onshape. No, for the cam capability.
Onshape? Oh, no, not Onshape, yeah, Onshape's free. Onshape's free for design.
For his, for cam,
For cam.
it's expensive. So yeah, so that they let you design for free, but when they get the G code, which is what tells the,
Yeah, you need the G code,
that's expensive.
but you,
Oh, I don't do,
you
yeah,
use it.
yeah. Brian's moved on to subtractive manufacturing.
And in theory, I could do aluminum, but I haven't bought any aluminum
Well,
block
good
or
thinking.
anything. Yeah, the robots, right?
I mean, you have the
Yeah,
bits.
yeah.
But aluminum's soft
Wow,
enough,
that's
it's not
gonna be
like
some-
steel.
Yeah, you can do
Beautiful
like
chassis.
aluminum,
Copper or something.
bronze, copper, but like,
Yeah, it wouldn't want.
some claim you can do some kind
Yeah,
of
copper.
steel, but like, I don't know. We're gonna get hot and break this, need them.
Can we pass these around?
Yeah, that's what they're here. They're just-
Okay.
I put both sides, so like I said, note that they're flattened with a flat bit, and then this was drilled, this was with
You,
what kind of
you
bit,
did
yeah.
your drawer design?
I took someone else's design and modified it a little bit.
And what's the 90-degree thing you're,
This.
90-degree?
Okay, so
Where?
on the other one, on the other robot, there's something with like, kind of like
A bevel.
a diamond shaped bit or a triangle shaped bit,
Triangle.
You can
and
see how square this one is.
yeah, that was a perfectly flat bit. The other
Oh,
one's got like a triangular shape.
Oh, I see.
V-bit.
That's
a
what you mean.
V-shaped head.
Like a,
It's a 90-degree V.
okay. Oh, so it makes a nice, it makes a different kind of a carving. right?
Yeah.
A different trench.
So I started with robots and now I'm making a fancy privilege board. So this is like.
I used to play.
But yeah, doing the aluminum and poly, except for the FRC team, we use like a Shaper Origin, which is a hand-driven one, you know.
Oh,
It's really cool.
like this?
It's a CNC, but you guide it, it's like augmented reality and a little screen. And you
Oh.
follow the dotted line. You load the model, they have a Fusion export model.
No.
And then the school got a Tormach. But yeah, breaking bits and, you know, they're much more technical.
Yeah,
3D printing.
I only broke one bit so far.
Yeah.
And it was an 1/8" bit, the same one that made that robot. I forgot to turn the spindle on and I was moving it around. And you're talking about how strong the motors are, it just snapped a bit right in half.
Oh, because I forgot to turn.
I didn't turn the spindle on and I was.
And
moving
they're
it, and
screwdriver, right? So incredibly strong.
Yeah, so it was the XYZ are incredibly strong and the bit is not that strong.
lot of torque. Yeah, so these aren't belt driven, they're meant to.
Yeah,
Yeah,
they're powering through aluminum, right? So
Yeah,
they're
But how,
strong.
but that, why, you had to turn something on to make it spin separately?
Yeah, 'cause I was using my own software.
Oh, so you wrote your own.
Yeah. Let this pass it around. Yeah, I did, actually, when would maybe I'll show that, cause it's pretty cool.
So you did this just for this project? Or-
Yeah, I did a version of Space Needle with my.
So, I mean, you wrote your own software as a
Yeah,
side project?
yeah, they can take a 3D model and turn it into a surface path or G code.
Oh.
Breaking drill bits are pretty common.
Yeah, CNC. CNC out, it got
But not the
some.
software.
What is the machine you're using?
It's a Genmitsu 3030 program.
Steph, could you put that link in the chat?
Yeah, it's like relatively inexpensive. It was like $700 or something for the machine, so it's not crazy, not like, it's like a 3D printer. But on top of that, you gotta worry about the materials and the software. Which are gonna add
Software
like,
could be 400, well, you paid 450.
something 350,
349.
349, that's what it was.
Is this a best?
And double for the pro
And-
version.
And
The
there's
funny
still-
thing is, that Makerspace version.
What you doing?
Oh, you-
Literally $99.
Oh,
Oh,
Oh, so you can, yeah, what's,
I could have bought it from. Okay, I didn't know that.
what's the entry level? Oh, Makerspace?
Thing about the Makerspace edition is you get one copy, they both like on a server that's attached to the machine.
Yeah,
And then you can install others that aren't able to run machine, but you can generate all of your files for like a Makerspace. So you can have other computers setting up
Oh,
jobs,
okay.
and then you take it over to the one that actually runs the machine.
Anybody can
Yeah.
buy that.
Yeah.
I am not connected to the machine, so I export an SD card. I walk my SD card over and I plug it in and I get this little janky little paddle,
kind of
which I'm making another one of those too, but.
sneaker.
But isn't that better
That's
stuff
right.
your computer doesn't like go to sleep or something?
Yeah, they say it's better, and then it's got this dedicated communication, so it doesn't get laggy or anything, so.
Well, you could get a Raspberry Pi, like a lot of 3D printer people. do.
Okay.
Like I have.
Next Saturday, there's actually a CNC,
Oh, I'm going to that.
club.
Oh.
That Rockler, they're gonna do CNC.
Yeah, you should.
Where's that?
Yeah,
Where's
yeah.
Rock?
It's in Orange, right?
Yeah.
I think it's
I
in
know
Orange.
that in the chatters.
He sent it to, it was broadcast on our mailing list, right? You sent it?
I don't remember
But
where.
I got the email, or I might have been from the meetup, but I joined the OC maker group. You should join there if you want to get their emails about events every month. Yeah, like that.
Right. Thank you, Brian.
All right, Brian, thank you.
Next up, Greg. Is
Okay, yeah. Share my screen. How do you share mine?
So on the bottom,
I'm sorry, Frank. It's at the bottom.
I see it. Okay, so this dovetails nicely with what Ethan was talking about. So I've been experimenting with brushless DC motor and controllers, and I went and looked for controllers for them, and most of what you'll find is off the shelf is either open loop or they require the Hall effect sensors to be built into the motor. And a lot of the motors I was looking at don't have the Hall effect sensors. So I looked around and I thought I'd share just my experience. I looked at ODrive, which used to be open source, but it no longer is. They went closed source. So I kind of ruled that one out. And I looked at BESC, and this one actually, I want to look further at it. And this is called Better ESC. And it's an active group, and most of the people that are working on this one are using them for like scooters and stuff. So they're building their own electric scooters or kind of improving the existing ones. What I settled on is another one called SimpleFock, and this is Arduino based. And it's basically a library which does what Brian was talking about, which FOC is field oriented control. And so what it does is it electronically changes the orientation of the magnetic field to make the motor rotate. So I actually wrote the code, and I got a controller. Let me show you. I settled on this controller. It's called the ESC V4.2, and it actually comes with ODrive software that gives you some of the specs, but it's got a microcontroller built into it. So it's an STM F4, 32F4 series. And so I just built a SimpleFock based program, and then I loaded it onto that firmware onto this. So SimpleFock, just to give you a little bit more about that, and then I'll show you the code. SimpleFock, the cool thing about it, and I think VESC is similar, what they do is they work to be agnostic. You can use any controller, you can use any motor, you can use any encoder. And if you have those things, you can actually make it work. You may have to write some driver code to make it work with their program. And actually, interestingly, they treat both steppers and brushless DC motors the same. If you have a stepper motor driver and stepper motors, it will treat it the same way and do a rotating field so that you can actually make it work just like a brushless DC. So the code is very simple. To set it up, you just tell it which pins and instantiate your encoder, give it some information about your driver, and then you link them together. And then there are different modes. I put it in a torque voltage control, which is basically like you are driving a DC motor with pure PWM. So it really behaves that way. So the code is very simple. That's it. And then there's a loop down here. A bunch of it's just test code where you just have basically those 3 lines in a loop. And then it actually does that. So I'll go ahead and use my high-tech color switch. And let's see, can you switch over to my video?
Yeah, go ahead and stop sharing and then I'll be able to highlight.
Oh, thanks. Cause I wanna go.
There we go. Okay.
It's in orange.
Go ahead and turn on your camera, or is there a? On your laptop, or?
I was gonna try to use my phone.
Oh, okay. Yeah, so when you join Zoom on your phone, it's gonna join audio automatically.
Okay, there we go.
Or maybe not. Okay, there we go. All right.
Okay, so here's the controller.
It's on mine.
And you can see this, the motor is right here. This is actually just a little drone motor. But the video is not important very quickly. So this is just a little drone motor. And then I made a little attachment so that I could use a belt with it. This right here is an AS5600 encoder, so it's a magnetic encoder. There's a little magnet you can't see, it's mounted to the shaft of the motor. So as the motor turns, it can read from the magnetic field what the angle is, and then it turns it, let's see, it uses that to set the field. So I'm gonna reset it. When I reset it, you'll see it move a little bit, and what it does is it has to know the relationship between the encoder angle and the electrical angles. And so it goes through a little calibration algorithm that it has where it goes back and forth to determine the direction, and then it sets the 0 as one of the different.
Okay, so your BLDC, is that it looks like it's a direct drive motor, but then you've got a belt. So
Correct.
what's your effective reduction between
1 to 10.
1 to 10? Okay.
And so I'm just gonna, so this, it's squeaking a little bit. I think it's a little bit. But I just give it essentially commands to say that was essentially PWM of 1 in one direction. And then I can go PWM of -1 and it will go in either direction. I guess the video doesn't look like it's up.
Oh, sorry, yes, yeah. But that squeaking, that's not a bug, that's a feature. Now it can't speak up.
Yeah.
It's the
And this is an audio broadcast.
No, it's on.
So, all right, so I just thought maybe someone else could benefit from, what I learned from that. So.
Yeah,
That's
for
why I was-
sure. So we can see what you've built. Like, was this purpose a technology demonstrator, or does this turn into?
I have some plans to go forward. I wanted to, I'm gonna get another motor and controller. My first thing was to see if I could get it to work, and
Okay.
so I've got to get another one of those, and I'll drive the other wheel as well. That's gonna make a little.
Okay, so it's like a halfway point. Like this is very cool. Very cool. And when you flip it upside down, does it have enough power to move?
Oh, yeah, yeah,
Okay.
yeah. I had to look to find it, 'cause a lot of the drone motors are high RPM. So this is one that I specifically chose is low RPM, higher.
Yeah, if you could, I've always been confused about this. the concept of KV.
Yeah.
With respect to needing to spin fast or needing to spin slow, like what does that mean? How does that work?
Okay, KV is a higher KV means for the same voltage, it will spin faster. And conversely, so I forget the term they use for it, but there's a 1 over the KV essentially is the torque per amp.
Oh, okay.
So, but you have to make sure it's in the right units, but they're very related to one another.
Okay, thank you.
That software, is it also working sensorless or does it require a sensor?
You can, so that's one of the cool things about this library is you can run it sensorless, so it's open loop. The problem, I actually bought one of the really cheap speed controllers that's open loop, but like I expect it to run into situations where it will have too much torque on it so that it won't be able to turn. And if it runs open loop, it sits there and it just keeps trying, it rotates the field, but the wheel's not turning, and so it kind of, the torque goes back and forth.
Cogging.
Yes, thank you. Yeah,
So it's much better with sensors, because
Yes.
cogging through a pain in the butt.
exactly. And there are ways, so I spent a lot of time researching this. There are actually tool sets to do it sensorless. They don't work at slow speeds.
I was gonna say, I had sensorless and the robot.
Right, yeah.
And then I upgraded the censored and it's just really nice and
Yeah.
smooth, just like yours is like what you're talking about.
Thank you, Greg.
All right, great, thank you.
Up next is Jim.
Yes, hi, hey, I wanna give an update on, Big Orange's progress in, the LLM space, which, I'm kind of following what Seth is doing on onboard robot, with tools and LangChain and everything. And, also, a future add-on I'm about to do with an NVIDIA board here, which is similar to what Alan's doing.
So we have a lot of new people in the audience. Can you orient us a little bit with everything that's on the screen right now? Because you've got a pretty cool setup.
Yeah, so, right. So for those of you not familiar with, Big Orange is my long-term project, with a fully voice activated, robot that can navigate around the house, avoid obstacles, interact with, people, objects, it senses distance, with the 3D, it's got a 3D camera, it's got LiDAR for 2D, it's got a depth sensor as well, I don't always use that, and then sonars, and a little claw here that can approach something on the floor and pick it up. Occasionally it works, but the idea, or it's built upon a lot of off-the-shelf products, including OAK-D stereo camera, which can detect objects and distance to things and depth and everything. That's hooked into the robot's sense system, so I can tell the robot to go up to a person and go up to an object, find an object even. And then the LiDAR system is called SlamTech. It's out of date now, but that was a store-bought or company purchased navigation system that I didn't have to program from scratch. And it helps you of obstacle avoidance and mapping and localization, all that kind of stuff. Non-ROS, it's using Windows API. Then, this base, this orange base was also off the shelf from a GF robot company. And it came with motors and the frame and the wheels and everything. So, but then I pieced together, you basically get some kind of structure like this you can buy off the shelf. And then you can put the layers of electronics and motors and everything that you need. It's it's a lot quicker than trying to do everything from scratch. And then a monitor up here. So, the main CPU is called Latte Panda. It's a it's an Intel-based Celeron processor. That's because I needed Windows, but it also runs Linux, no problem. It's also from well, Latte Panda, you can look it up. It's sold. Also GF Robot sells it. And those are, and they're all low power. Everything here is low power. It's 12-volt battery with 5-volt as well coming out of it, big lithium battery, and then I've got a second battery too, with 12-volt. So 12 and 5 volts runs everything, and the battery lasts for a fair amount of time. But when you're running, you know, it'll deplete it quicker and quicker these days. And this thing here coming soon, I've got it blue tacked, but this is the NVIDIA Jetson Orin Nano 8 GB, which has a really good GPU on it. It's only $250 for this. So it's a lot lower price than even good video cards for PCs. And this one, it's 8 GB of video RAM, and that can run all sorts of great NVIDIA models, including real-time stuff. So I'll mention that at the end here, because that's sort of the future that I'm working on that haven't realized it yet. So that's the background. And
Are you replacing your Panda with the Jetson, or are you just, no, I mean,
no,
have more
currently
horsepower?
it's currently, yeah, this has got like at least a 4-core ARM processor with the GPU, but I'm using it, gonna use it just for processing the camera and,
Okay, so
camera
complementary, so they're gonna work together.
yeah, they're gonna work together.
Okay.
I don't plan on replacing that, well, I can't, actually, for this setup, I have to have Windows. This doesn't run Windows, it runs Linux. So I'm not gonna move over to the Linux version of Slamtech. I don't think I don't think I can. Yeah, yes,
I'm just curious, how did you manage to get one of the Jetson or Nanos?
yeah, they were hard to get. I mean, yeah, I don't, I mean, you may have difficulty getting one of these. I'm sorry to, to sort of be the lucky one that got one, but I ordered in December in a back order, and it took until April to get it. And it was back ordered from I forget which company, but it was one of the main ones listed. And then I think the tariffs threat came, and they said, we're not accepting any more back orders. But I don't know, the tariff is kind of up and down, so maybe they would, but other people have been waiting for these for a long time. If you have some more cash, you can just up to $700 and buy what Alan has.
Yeah, the Arrow does
16
have a
gigabytes.
stock of the NX Orin 16 GB, but you're in a whole different price.
It's
point.
700, right?
Yeah.
So yeah, it's a bit pricey. But in any case, yeah, I'm glad to have this. It's really perfect for this platform. But that'll be coming in a future, future show and tell. For now, back to the screen here, I wanted to show that, what you're seeing here is a view from the Oak D camera, stereo camera, and with a YOLO model running for real-time object recognition and also 3D coordinates or depth sensing plus 3D coordinates. This is what I use to have the robot go up to some person and all that, because and identify an object. So this is something I've had for quite a while, several years now, and this is not a new model or anything. But what I'm showing now, or what I wanted to touch on today, is my use of LangChain is new, and with tool and memory use, kind of like what Seth is doing. So let me switch over to a video so you can see that the background is that I want to be able to control the robot with high-level human commands and use an AI agent to make to take the complex request from the user and turn it into robot tool commands that the robot can actually execute. So that's what an LLM can really do better than an if-then statement. my existing system just says, if the user said, open, go to kitchen, if the user said, take a picture, if the user said blah, 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 and it has to be exact text, right? This type of, using an LLM opens up a huge possibility, of having it create the plan to do whatever the complex task is. So let's just go to the video then, to show you what I'm talking about here. Let's see. What is it? Okay, let's go to, I don't know if I'll share the audio. Try sharing again. Here. Video. Okay, so here's the video.
Hey Orange, drive in the path of a square of 1.
It's not working. Oh.
Oh, yeah, not on the YouTube video, but on.
Let's try it again.
Hey Orange, drive in the path of a square of 1 meter sides.
Jim, pause it, minimize the screen. Go out of full screen, take it out of full screen, right down at the, on your computer. Yeah, mute that guy.
Yes. I don't think it was causing a big problem.
Hey Orange, drive in the path of a square of 1 meter sides.
So here you're looking at the map of that Orange was created for the road. Now what you're seeing is my command is going to the line graph system, to the agent.
Yes.
Yeah. Now you see it planned out, those 4 points. And there's no code for this. It's doing it completely through the LLM and it converts it to a list of points. I added a new routine to the rolling code that goes through a list of points.
By getting tempted.
So here you'll see the output.
Here you can see the model has set the various points and decided that it has successfully moved in the path of a square using line graph.
So the caveat there is that, the more detail is that it called the position, get pose of robot, so it knows the XY of the current location, and then it will do the math to calculate those 4 points and then submit them based on, from the point where the robot is currently. It then, you can give it more and more specific instructions, like to tell it where it is, like you're currently in the middle of the square, or I just wanted to just start going forward from where it is. But essentially the LLM is converting that command into actual programmatic calls. So it's making its own algorithm from that.
So it does the math to figure out where the square is? The
Yeah.
LLM does?
Yeah, the LLM's doing that.
Wow.
Yeah, and now what's interesting about that is, I could go on for a whole lecture on this, but I basically had to, I refined it since that video was done, and I gave the prompt a lot more detail for the, instruction, for how to handle, those commands. Especially for the, for relative motion commands. So if you see, you can see here from, again, this would take a lot more time, but I had to tell it, if you tell the robot, go forward 1 meter, then take a left and go 1 meter, it might not know what it might do the wrong thing, because it's a little confused. So I gave it a bunch of instruction here of conventions, like yaw of 0 means robot faces the x-axis. Stuff like basically the coordinate system, I had to explicitly tell it, if yaw ever greater than 180, then subtract 260. This makes it a lot more stable, so then I can tell it things like, go forward this amount and then take a right turn, and it will do it correctly, no matter whether the robot's facing 180 degrees or 0 degree, whichever way it's facing, it'll do the proper delta. So that from the point of view of the robot. Anyway, that's just a side thing. So that's the land graph. I can actually run, well, yeah, you saw kind of how that works. Another update is, I took Brian's advice and I added, so for my prior demo was, find the closest command. So like if you give Orange a command that's not the exact command, it will, it looks up a close command. Let's try one. Oh. Hey, Orange, open up the depth window.
Open depth window. Okay.
So it's using, as Seth recommended, there's the depth window. Hey, Orange, close the depth window.
I assume you meant close depth window. Okay.
Pretty cool.
So, what I'm doing for each of these commands now, is I'm adding the words user gave command to robot in front of the command before finding the embeddings, before getting the embedding vector for that command. So if you just say, if it's like a 1-word command, then at least it knows that that was a robot command, and all the, so it works better. Let's just say it works a lot better. Or it will work somewhat better, I'll say, I don't know how much, but it's definitely a little bit, definitely better to give this extra context. And all of the distances went way down. And I also added if the command is if the distance is above a certain amount, then I ask the user, did you mean such and such? So that is let's try this. Hey, Orange, capture the scene.
What do you mean? Goodbye.
No.
See ya.
No.
It sounds like you're referencing something specific.
Oh.
Could you clarify what you mean by after the scene? I'd be happy to help.
Hey, Orange, capture the scene.
I assume you meant take a picture.
Okay,
Here's the picture I took.
that one is chicken, but you saw how it, you saw it go through that, asking the user if he meant. That's all I wanted to just show you. So yeah, so that's that, and here I can show you one other thing of how let's give it. It's not going to be able to move the motors off, but you'll see some output here. Hey, Orange, go forward 2 meters. Oh, that's not what I wanted to say.
On the table?
Yeah, dude.
No, it's not. It's not. I just.
Okay, I know,
I just said it's not gonna move.
We've never done that.
Let me think about it. Hey, Orange, drive 1 meter forward, take a left and go 1 meter. So here you can see, it's kicking in.
We have the designated movements. I'll advance 1 meter forward, turn to the left, and then go another meter. I moved 1 meter forward, turned left, and proceeded 1 meter in that direction. What would you like me to do next?
All right, so you're seeing like all the talking is happening at once, but the key thing to look at here is, after I gave it the command, it called get pose from the LLM, and then it plotted a course with XY. So that's using the tools. And then I'm printing out the tool calls here. See, it says get pose and move through locations. So those are the actual calls. And then here's the AI message. So that's, yeah, anyway, so that's how that's working. I also added this, yeah, so anyway, and that's pretty much the update. And one other thing is now everything you say to the robot is getting recorded in the history of messages, whether or not it gets sent to the agent or not. So when you give a command to Orange, it can be my old code just handles that command directly. Say it parses it. It says if the user said go to kitchen, and then it just says okay, do it. It never makes it to the agent. If the robot doesn't understand, if my if then else why, if my long list of command checks does not match anything, then it sends it to the agent. Then the agent can use the tools to do something or whatever. But this is sort of an old system and a new system kind of living together for the time being. But I want that context. So whatever commands you give to the old system, I'm now gonna keep those in the chat history so that if you ask the robot, if you ask what commands have I given or show the log, then it'll show all of that. And so like, hey, Orange, show memory. Oh.
That's my name. Don't wear it out.
Hey, Orange, show memory.
Didn't you mean reset memory?
No. Sorry, I
Able to correctly show memory is a command. However.
Okay, that's my fault.
Past interactions we've had in this session. Is there something specific you want to know?
That's my fault. I didn't have the right, command, oh, yeah, there it is. Reset. See, this is a case where, yeah, you have to like, it's hard to get all these different cases working, unless you have to, I don't know. There's so many different combinations. Oh, hey, Orange, show chat log. So yeah, this will show the entire log of what we've been doing. Let's go. Is this it? So going backwards, you can see show chat log, and then it's showing you what the robot said, human. And so there's a full log here of everything, even if it didn't go to the AI, through the AI system. So like capture the scene, it just did it. It just took a picture. So anyways, that's oops. That's all I had for that. I've been working heavily on this to try to get more complex behaviors to to leverage the AI. do that.
Are you building? I know you're building a chat log. Are you passing that to the LLM so it has context of like what's been happening recently?
No,
Or-
this is all, okay, I'm sorry, it's trouble communicating, but when I say that, I'm using LangGraph and I'm using the LangGraph state. And all these messages are, I'm capturing everything. All those messages are in the LangGraph graph, which gets sent to the LLM every time.
Okay, so that is, so this
It's
getting the history.
official, it's official history, and all of it's being used. So if you ask the robot something like, did I ask you to go to the kitchen? It'll remember that and tell you.
So I've got an amazing idea for you. After we go through, I've got something that you might really like to sink your teeth into after this.
Yeah, definitely. And the future is kind of incredible because with this device now, I've been I went through a tutorial that has something called Lava, and it's a vision transformer with along with so it's a VLM and with a vision transformer and a clip algorithm or clip model, so it can for video. So it can take in up to around 3 frames a second and tell you what it's seeing or answer a question about the scene. So you could say, and then there's another add-on with RAG. So you could you could say, here are my keys. And then say, remember that, and it will add it to a RAG. Then you could go hide your keys around the house and say, go find my keys. Now it'll drive around. When it sees the keys, it can identify them and then say, the keys are in here, in this room, wherever I am. So that's what you should eventually do with this. That's what I'm kind of excited about.
Man, looking good. Thanks, guys.
Man, amazing.
Catch up with me.
Yeah.
All right, up
Stop share.
next is
Thank
Ross.
Oh, okay. Great. That was fantastic, Jim. It's been fun to watch your progress on Big Orange going back, oh gosh, 4 or 5 years when it went up and picked up bottles and whatnot. And now you've got somebody you can talk to and discuss the matter with. Neat. So what I've what I thought there'd be some interest here today is the completion of a project that me and a couple of other experimenters have been working on, namely getting a Raspberry Pi camera to work on the relatively new Raspberry Pi 5. For anybody that's on ROS 2 Jazzy, which is the current distribution. For anybody who's tried doing what I've just mentioned, you've probably run into a problem. Raspberry changed some of the drivers and the kernel on the Raspberry Pi 5 that made the way you dealt with a camera up to now not work. So and there was some workarounds that we found, and anyway, as a couple of us made it a project to formalize, to do some experiment. We were successful, and we decided to make a GitHub document that is more universally available and mention the availability of that document that describes how to install the scripts and libraries that are necessary to make this thing work. Anyway, what I'm actually specifically talking about is the Raspberry Pi camera. Let me just quickly show that here. Hopefully this works. Right. Right. So this is my TurtleBot. It's the whole TurtleBot, and this is the Raspberry Pi camera that is used. That many of you will probably recognize that. This is a version 2.1, I think, that I've actually had for 5 or 6 years. So so what I'm talking about, in summary, a bunch of us prepared a document that other folks can use
to get their camera working. And I'm going to share something. I'm going to share my desktop and show the document. We'll move on from there. Hopefully this will work, as they always say. Right. So this is a post that was on the Open Robotics discourse.ros.org yesterday that I put together. This is me, and we published this document on this repository. The purpose of the event, as I've mentioned, is to get one of the three versions of the Raspberry Pi family camera working on a 5, equipped with Ubuntu 24 and ROS 2 Jazzy. The end purpose was to get an existing package already released by developer Christian Roche, called Camera ROS, that actually will with Raspberry Pi 3 and 4 work perfectly well. But as I mentioned a moment ago, if you thought you could use the packages that were available for 3 or 4 to work on a 5, it wouldn't. So if anybody's working on the camera, simply have a look at this post available on the ROS discourse.ros.org, and if you click that, you end up on a document on my public repository that just describes how to install it, and it's actually surprisingly complicated. It's too bad that you can't just run a couple of scripts and get the damn thing to work, but it doesn't quite work out that way. But anyway, the 4 of us working on this put together. I'm not going to go through these steps here, but we've been going over this with a fine-tooth comb. Hopefully it will work with anybody that wants to try it. You end up installing some stuff. You end up messing with the config.txt file that lives on the SD card on the Raspberry Pi. There's some very specific there's very specific parameters you have to set. If you don't do it right, it won't work. And when you if you do these things right, you can get one of the 3 available cameras to work. And that's kind of it. And let me just unshare this and share something different.
So Russ, would you mind pasting the link to the OSR article in your GitHub in chat for us?
Sure. Yeah, absolutely.
That would be great. I'd love to read up on it.
Pardon me?
I'd love to read up on it. Thank you.
Yeah, it's if you've had trouble getting the camera to work, we're pretty sure this will help you out. So if I'm trying to find a specific. I've actually got a screen. I'll show this one, I guess. Oh, this is my whole darn desktop, but over here on this corner is what you're looking at here. Sorry about this. This is my Ubuntu 24 desktop displaying the image from the camera, the objects that are across the room. I was sort of hoping to go behind it, but I guess it's not going to let. Oh, there it is. Whoops. This is actually live, but my system bogs down a little bit. So the whole point of what you do is you run. This is that's okay. So this is my desktop. This is a window that is SSH connected to my Raspberry Pi 5 that lives on the side of the room. When you run this command, this is the camera ROS command. It'll display that image. Ta-da! So I'll do that, post it so you can all see it. Thank you for your indulgence. You're welcome to correspond with me if you need any details on some of the nitty-gritties that are involved there.
So why Wi-Fi is not compatible with this? Did they explain it somehow? Do they release new cameras or something?
Yeah, the problem is they changed Raspberry Pi changed the underlying kernels to that made and created some libraries that are specific to those kernels if you run a Raspberry Pi using their OS.
Okay.
If you try and use the available ROS packages that worked before, they don't anymore. But so what we did, actually it was Walter Werther. He created a set of libraries that you can download or install on your machine that replace the libraries that actually update the libraries that worked with Raspberry Pi 5 or 4. So there's the essential part of what we're making available. What was made available is a set of libraries that work with the new kernels, and the instructions just show you how to use Walther's Marco's. I should say Marco Walther's his name. Marco's libraries. Okay. Any other questions?
And looking good. Thank you. Thanks for sharing.
Good.
It seems like a lot of effort has to go into support those Raspberry Pi cameras.
That's crazy.
Even I hit. I mean, on this NVIDIA Jetson board, it's like took me all these hours to figure out how do I,
Was that MPI or USB? Like which
No,
one?
I'm talking about Raspberry Pi cameras. I thought are defined by the SPI or
Yeah, okay, the camera finisher.
it's SPI, isn't it?
That was MPI. I don't know. I don't know that.
Yeah. Anyway, that connector goes through hardware and drivers and stuff, and if they're slightly askew, nothing works. And I just
Right.
plug in a USB desktop camera, and everything's fine. You know, of course. And
Yeah,
also
I know.
all the NVIDIA examples work with the desktop USB camera, just a simple camera. You just plug it in, it works. So I'm not sure the advantage of that Raspberry Pi is.
USB. That's right.
Yeah, that's
Actually, if the truth be known, there's my newest project, which is upgrading an old Turtlebot to work with Jazzy 5. I'm using an Oak D Lite camera with a USB connector, and yes, it's way easier to use. The reason a bunch of us get bothered to spend this time up with the Raspberry Pi camera is that it's inexpensive. You can buy them you can buy the clones for $16, which is what I did when I started into this project, just to have something to test with. And but it is a bitch to get the damn thing to work.
Yeah, and also the Oak D, that's using USB. If you use it with USB 3 speed, I get 30 frames a second to my
Yes,
Windows.
that's right. Yeah.
Yeah.
At 4K, or I don't know.
And so this is something that I ran into years ago with InMove, because I'm like, I'm just going to use 2 cheap USB cameras in the eyeballs, right? So I put 2 of them in, USB cameras, claimed frame rate of 30 frames per second. Yeah. But and this could have changed more recently. We're talking almost 10 years ago now. But USB 2 cameras generate MPEG compressed images and pass them over the USB 2 wire over a certain bandwidth. And everything is optimized for a static screen. with something smaller than the full screen moving within it, right? So you're only compressing some delta, which is some small percentage of the whole image. Now, if you're on a mobile robot, your whole field of view moves at the same time. And for those cameras, my frame rate went from 30 to 3, just because that whole camera's reason to live was keeping track of a bobbing head in a static background. And mobile robots don't have that luxury. So maybe with USB 3 cameras and some of the more modern ones, it's less of an issue.
Yeah, I think the USB is, you know,
A lot faster now?
yeah, we're talking
Oh, wow.
5 gigabits per second is what is USB 3 is capable of.
Yeah, that's nice.
So tenfold increase over. So yeah, so that's, I've been happy with those cameras and they're just plugged into USB, yeah.
Yeah,
Thank you, Ross.
All right.
all right, my
Uh,
pleasure.
Sorry, that was the last show and tell. So after this, it's all open mic. Anybody that wants to